Hello dear students, we are discussing the lesson oscillations. In that we are going to discuss about the oscillations of a simple pendulum in simple harmonic motion and its laws, the laws of simple pendulum. Before speaking about the oscillations of simple pendulum, as you know very well, the differential equation for simple harmonic motion is t square x by dt square plus omega square x is equal to 0. Or otherwise I can write d square x by dt square equals minus of omega square x. If I get this form, then this gives you a linear differential equation for simple harmonic motion. If I am going to get an expression like this for the oscillation of a simple pendulum, then I can say the oscillation of simple pendulum is also simple harmonic, is also a simple harmonic motion. As you know very well, the acceleration must be directly proportional to the displacement and it must take place in a direction opposite to the direction of displacement. The negative sign in this expression indicates that the acceleration is in a direction opposite to that of the displacement of the object. So if this expression, if this condition is satisfied, then we can say the oscillation of a simple pendulum is also considered to be a simple harmonic motion. A simple pendulum is nothing but a mechanical system which executes periodic motions. What is periodic motion? Anything that happens repeatedly during fixed time intervals, then we can simply say it is a periodic motion. So simple pendulum is nothing but a mechanical system which brings out periodic motion, which executes periodic motion. Let us consider a metal bob of mass m, which is suspended or fixed to one end of the string. The other end of the string is kept supported by means of a metal rod, which is attached to a stand. This is fixed onto a stand. This is fixed. Metal bob is attached to one end of the string and the other end of the string is fixed to the metal rod or otherwise to the stand. In the state of equilibrium, the metal bob or the string along with the metal bob will always stand vertically downwards, which acts vertically downwards. It will not move here and there or to and fro. So we can say the state where the forces are said to be balanced and the pendulum, which is suspended vertically downwards, is termed a mean position or equilibrium position. In this diagram, this is the mean position or equilibrium position. Now, if the bob is displaced to some extent, through some distance or is displaced through some distance, let us say x, or through a distance, let us say s, then what will happen? The bob will return back towards its equilibrium position or mean position. The bob will oscillate about the mean position. It will move towards the mean position because of velocity gained by the bob. It will overshoot and will be moving towards the other end of or other side, and then the velocity will become 0 at one point. Then once again the bob will return back towards the mean position. In this way the oscillations will be executed. Due to air resistance, the oscillations will be gradually, the amplitude of the oscillations will be gradually decreasing and then finally it will become 0. Oscillations will die out. This is how the oscillations will take place in a simple pendulum. Now, if the bob is displaced from its mean position, the bob will be returning back towards the mean position. And because of the velocity gained by the bob, it overshoots and oscillations will be executed. The bob will be undergoing oscillations. Let us say L be the length of the simple pendulum. The length L will be measured between the point of suspension of the pendulum and the center of gravity of the metal bob. So whenever you measure the length of a pendulum, the length must be measured between the point of suspension and the point of center of gravity of the metal bob. So L is the length of the pendulum. Now, if this pendulum is considered, the pendulum is acted upon by two forces. What are the forces here? I can show you here. The pendulum is about its mean or equilibrium position. If the pendulum is displaced through an angle theta, small angle theta, then the pendulum will be at its new position. On this pendulum, there will be two forces acting. One is gravitational force mg, which acts vertically downwards. It's a gravitational force which acts vertically downwards. So gravitational force acts on the body. Gravitational force acts on the body, which acts vertically downwards. Another force is the tension, which is acting along the string to the point of suspension. So the second force is the tension T acting along the string to the point of suspension. So two forces are acting here on the pendulum. One is mg, the gravitational force, which is acting vertically downwards. It acts on the body of the bob. And the tension T acts along the string to the point of suspension. So these two forces are acting on the entire arrangement, the simple pendulum. Or in other words, I can say one is acting on the body of the pendulum and another one is acting along the string. Which one? mg acts on the body of the pendulum. Tension T acts along the string to the point of suspension. Now, this mg can be resolved into two components. One is a normal component which acts along the string, and the other one is a tangential component. I can say this is normal component. Normal component, which is nothing but mg cos theta. Why? If this is theta, this angle is also theta, then this component must be mg cos theta component. And this one is mg sin theta component, and this mg sin theta component is nothing but the tangential component. mg sin theta component is the tangential component. So this normal component mg cos theta component acts along the string but in a direction opposite to tension. Normal component acts along the string but opposite to the tension T. Tangential component acts perpendicular to the string, and is tangential to the arc length. This is the arc length. Actually, this is the arc made by the simple pendulum as it is displaced from its main position. So the tangential component acts tangential to the arc length of the pendulum. So it acts tangential to the arc length of pendulum. What is this normal component? It is mg cos theta. What is this tangential component? This is mg sin theta. mg cos theta is the normal component, mg sin theta is the tangential component. And we saw how they are acting. One is acting along this normal component, mg cos theta is acting along the string but in a direction opposite to tension. And then the tangential component mg sin theta acts perpendicular to, this is otherwise called the perpendicular component. This is the parallel component, vertical component, horizontal component. Here this mg sin theta is the tangential component which acts tangential to the arc length or arc distance made by the simple pendulum. Now we can say here this normal component mg cos theta is acting in a direction opposite to tension. Now we can consider this diagram as a free body diagram, and then we can apply the amount of forces or the number of forces acting on the body, and then we can equate it with the product of mass into acceleration on the basis of Newton's second law, from which we can bring out the expressions. As you know, this is the rule for free body diagram. Whenever you speak about free body diagram, first consider the body as a point, then mark all the forces acting on the body, then equate the forces to the product of mass into acceleration. Here we can calculate the acceleration of the pendulum on the basis of its oscillations. We can say L is the length of the pendulum as we have shown it in the diagram. Once again I can say L is the length of the pendulum. The length of the pendulum is measured between the point of suspension and the point of center of mass. That we know. Now we can bring out the condition, or we can check out whether this oscillation of a simple pendulum is simple harmonic or not. Now we shall go on. This normal component mg cos theta is acting along the string but opposite to the direction of tension. So in the first case, I can say T minus of mg cos theta, because mg cos theta is opposite to tension. So tension is one force, mg cos theta component is the another force acting on the metal bob along this particular direction. And this force, net force, is equal to the product of mass into acceleration. So we can show it like this. T minus of mg cos theta equals m into, we can speak about the magnitude. And then I can write T minus of mg cos theta is equal to m into, what is this acceleration here? Acceleration is centripetal. Acceleration is centripetal. As there is an arc distance covered by the metal bob, we shall say this movement of the metal bob describes a circular motion. We are considering the arc of the circular motion alone. So we can say the acceleration which is taking place due to this normal component is centripetal. So we can say here the centripetal acceleration can be written as mv square divided by L. As centripetal acceleration A equals v square by r, v square is as it is, r is replaced as L, where L is the length of the pendulum, which is equal to the radius of this entire circular motion possessed by the pendulum. Circular motion possessed by the pendulum. Now, what is this V here? V is the speed of the bob. V is the speed of the bob. V is the speed with which the bob is said to be moving or displacing. So A equals V square by R, and this V square R is replaced as V square by L. So the expression goes as T minus of mg cos theta equals mv square divided by L. This is one. This is equation 1. Now, you can see the tangential component here. The action of tangential component is acting tangential to the arc length and is directed towards the mean position. See this one? This arrowhead, this component is directed towards the mean position. So, what you can say is the tangential component of this gravitational force always acts towards the mean position. Always acts towards the mean position. That is, the direction of the tangential component mg sin theta is always acting in a direction opposite to that of the direction of displacement. Because if I am taking the pendulum towards this direction and displacing it towards this direction, this force, tangential component force, is acting opposite to the direction of displacement. So what can we say here? This tangential component is now behaving as the restoring force for the bob to come back towards its mean position. So the tangential component acting on the metal bob is the restoring force acting on the metal bob. So this one is for the normal component. For the tangential component, I can say the tangential component provides the necessary force to restore the bob back towards its mean position. Hence, we call this as restoring force. The tangential component is considered as the restoring force. What is this restoring force? How many number of forces are acting on the metal bob along this tangential direction? See, only one force, mg sin theta alone. No other force is acting on this metal bob. So, I can say here, the force, which is nothing but the tangential component, or which is the component perpendicular to the string, PS, FPS, and this is taken as FAS, which is acting along the string. AS stands for acting along the string. This is FPS, force acts perpendicular to the string. So this tangential component, which acts as the restoring force, can be expressed as FPS is equal to mg sin theta. FPS equals mg sin theta, but it has to be introduced with a negative sign, minus of mg sin theta. And this force must be equated with the product of mass into acceleration as per Newton's second law. This idea is very clear. I am applying FBD for this particular diagram. I just applied it for the normal component, and now I am applying it for the tangential component. I am saying here that tangential component is nothing but the restoring force acting on the bob to bring the bob back towards its mean position. So FPS, the force which is nothing but the component perpendicular to the string, is represented as mg sin theta, but I am introducing a negative sign here. What is the significance of this negative sign? Negative sign indicates that the force acts opposite to the displacement. The force acts opposite to displacement. S stands for displacement. So FPS equals minus of mg sin theta, which is given a negative sign. Negative sign indicates that the force acts opposite to the direction of displacement. Displacement is taking place in one direction. In this diagram, displacement is taking towards the right, but the tangential component is acting towards the left. If suppose the bob is moving towards the left hand side or left hand, then displacement is taking place towards the left hand. The restoring force will take the body back towards the mean position by acting in the right direction. So we can say the tangential component, which provides the necessary restoring force for the bob to return back towards its equilibrium position or mean position, always acts in a direction opposite to that of the displacement. Now only one force is acting on the bob along this direction, so I am taking this as minus of mg sin theta. I have to equate it with the product of mass into acceleration. So I can write minus of mg sin theta is equal to m mass into acceleration. This can be taken as m into d square s divided by dt square, which is nothing but the second derivative of displacement. Acceleration is nothing but second derivative of displacement. So I am getting the expression minus of mg sin theta is m into d square s divided by dt square. Minus mg sin theta equals m into d square s divided by dt square. What is this s? S is the arc length, which means it is the displacement made by the bob from its mean position to the extreme position. So displacement, linear displacement is S. I have to represent this linear displacement in terms of angular displacement theta. What am I going to do here? I am going to convert the value of linear displacement in terms of angular displacement, and I can make this I can calculate this on the basis of an approximation, considering that this angle theta is small. If this angle theta is small, I can consider this approximation here. What can I do here? If this diagram is considered, this is the angle theta, this is the displacement S, this is the length of the pendulum L, and what we want to do is we have to convert this displacement S, linear displacement, in terms of angular displacement theta. So from this diagram we can say angle equals arc divided by radius, L divided by S divided by L. And what is this? S L theta. I am getting the relation between linear displacement and angular displacement. S equals L theta. So I have to replace this S as L theta in the equation 3. So I can rewrite the expression as minus of mg sin theta is equal to m into d square L theta divided by dt square. L is constant, I can take out, m can be cancelled from this expression. Minus of g sin theta is there. This is equal to L into d square theta divided by dt square. D square theta divided by dt square. I can reconstruct this equation as d square theta divided by dt square is equal to minus of g divided by L into sin theta. Minus of g divided by L into sin theta. If you look at this expression, this expression has, this differential equation has a term sin of theta. This has a term sin of theta. The sin of theta varies sinusoidally, as you know, varies sinusoidally. So this equation is a non-linear differential equation. We are concluding here as a non-linear differential equation. In other words, I can say it is a homogeneous second order differential equation, non-linear differential equation. Homogeneous second order non-linear differential equation. What we need is an expression for a linear simple harmonic motion. So I am going on with this same approximation. If I consider this angle theta as a smaller one, then I can say sine of theta can be approximated to theta. Sine of theta can be approximated to theta. As we discussed in the previous classes that sine theta is approximately equal to theta is obtained from sine series. If theta value is very small, the higher powers of theta can be neglected and we can hold theta alone for this series. So sine theta is approximately equal to theta. If you do it for cos theta when approximated for smaller angles will be equal to 1. Tan theta when approximated for smaller angles will be equal to theta once again. Now our intention is to transform this sine theta in terms of theta. So sine of theta is approximated to theta. So this equation 4 becomes d square theta divided by dt square is equal to minus of g divided by L into theta. We just look at this expression. This is equal to or similar to that of the expression what we saw earlier, d square x divided by dt square is equal to minus of omega square x. In terms of x, linear displacement, I am having angular displacement. In the position of acceleration, linear acceleration, I am getting in terms of angular acceleration, d square theta divided by dt square. These are all similar. In the position of omega square, I am having g divided by L. The position of omega square, I am having g divided by L. So I can give out the value of the angular frequency, which is nothing but the natural frequency of oscillation of a simple pendulum, as omega square is equal to g divided by L. You can write this as omega square is equal to g divided by L, which is nothing but the natural frequency of oscillation of the simple pendulum. So this expression goes as d square theta by dt square is equal to minus of g by L into theta, which is nothing but the equation for the simple harmonic motion, which is similar to that of the equation for simple harmonic motion. From this expression, we can obtain the value of angular frequency. On comparing this with the expression d square x divided by dt square is equal to minus of omega square x. If you compare these two equations, you will have omega square is equal to g divided by L, which is nothing but the natural frequency of oscillation of the simple pendulum. Omega is the angular velocity. So omega is equal to square root of g divided by L, which is in terms of radian per second. We obtained the value of omega. So whenever you speak about the oscillation of any system, the very first thing what you are advised to do is you first check whether you are able to get an equation which is similar to that of the standard second order differential equation for oscillations or simple harmonic motion. If yes, then you can obtain the natural frequency of oscillation of that particular system by calculating the value of omega. After calculating omega, you can calculate the value of frequency from it. And with the help of omega, same omega, you can calculate the time period of oscillation of the system. Here the system is simple pendulum. For the simple pendulum, I am obtaining an expression as d square theta by dt square is equal to minus of g by L into theta. Once again, I am telling you this is done on the basis of small angle approximation. Small angle approximation is nothing. Sin theta is approximated to theta. That's it. So when you do so, you will be getting the expression similar to that of the second order differential equation. So from which I am calculating the natural frequency of oscillation of the simple pendulum. Natural frequency of oscillation of the simple pendulum. From this expression, I can calculate the value of f. Omega equals 2 pi nu. Omega equals 2 pi f. Or f is equal to 2 pi omega. Omega by 2 pi. F is equal to omega divided by 2 pi. So f is equal to 1 by 2 pi into root of g divided by L. This will give you the frequency of oscillation of the same simple pendulum. This will give you the frequency of oscillation of the same simple pendulum. Also, we can calculate the time period of oscillation. time period of oscillation of the simple pendulum. T equals 2 pi by omega. Time period equals 2 pi by omega. This is obtained from the expression angular velocity equals angular displacement by time. Time period came here and then angular velocity is taken to the denominator. So T equals 2 pi by omega. Once again, T equals 2 pi divided by omega is root of G divided by L. Hence, we can write T equals 2 pi into root of L divided by G. Frequency is in terms of hertz, which is the unit of frequency, and time period is in terms of seconds. So all the quantities must be expressed with their respective units. So T equals 2 pi into root of L divided by G is the expression for the time period of oscillation of a simple pendulum which is executing simple harmonic motion. If simple pendulum is considered or is taken as a body which is executing simple harmonic motion, then its natural frequency is omega equals square root of G by L. Its frequency is 1 by 2 pi into root of G divided by L, and its time period is T equals 2 pi into root of L divided by G. Based on this equation for period of oscillation of a simple pendulum, we shall now speak about the laws of simple pendulum. We shall now discuss about the laws of simple pendulum. Its dependence on the following laws or following factors. Instead of saying laws, I can write following factors. That will mean a lot. So, what are the factors to which this time period of oscillation depends upon? That is taken as the laws of simple pendulum. If you look at the expression T equals 2 pi into root of L divided by G, at a given place, the time period of oscillation is directly proportional to square root of the length of the simple pendulum. Time period of oscillation is directly proportional to the square root of length of the simple pendulum. This is termed law of length. This is termed law of length. Means time period depends upon the length of the simple pendulum. So, at a given place, in the sense the value of G is kept constant, or the value of G is not varying at that place. So, by keeping G as a constant one, means or by considering that particular place, time period of oscillation is directly proportional to the square root of length of the simple pendulum. T is proportional to root of L. We used to call it the law of length of the simple pendulum. This is the first one. And second one is law of gravity. We can say here law of acceleration due to gravity. Law of acceleration due to gravity. Here, for a fixed length of the pendulum, which means I am keeping the length L as a constant. The time period of oscillation is inversely proportional to square root of the value of acceleration due to gravity. So, law of acceleration due to gravity is nothing. For a fixed length, the time period of oscillation is inversely proportional to square root of acceleration due to gravity. So, time period of oscillation for a fixed value of acceleration due to gravity is directly proportional to square root of length. For a fixed length, time period of oscillation is inversely proportional to square root of gravity. So, time period of oscillation of a simple pendulum depends upon the length of the pendulum and the value of acceleration due to gravity. Greater the value of length of the pendulum, greater is the time period of oscillation. What is the meaning for that? Time taken for one complete oscillation will be more if the length is increased. And then 2, if the value of acceleration due to gravity is more at a particular point, the period of oscillation is less at that point. What does this mean? Where do we say the value of acceleration due to gravity is more? As you move from equator to pole, at the poles the value of acceleration due to gravity is more. At the equator, the value of acceleration due to gravity is less. If the same experiment is performed, oscillation of a simple pendulum is performed on equator as well as at the poles, you will get different measures for the time period of oscillation. The time period of oscillation will be more at the equator and will be less at the poles, because T is inversely proportional to the value of square root of acceleration due to gravity. And then, as we saw, the laws of simple pendulum depends upon the following factors. There are some other factors to which this laws of simple pendulum is independent. So, What are the factors to which the period of oscillation of a simple pendulum is independent on? We can see here the time period of oscillation depends only on the value of L and G. So the time period of oscillation has no dependence on the mass of the object. See, in this expression we are not getting any term like mass, which means the time period of oscillation of the simple pendulum is independent of the mass of the object. So we can say whether an ant is suspended and is made to swing at a given place, or an ant is suspended and is made to swing at a given place, both of them will give the same period of oscillation. Both the oscillations will be giving you the same result. Means the period of oscillation for the swinging of the elephant and the swinging of ant will be the same, which means this behavior is similar to that of a free fall. What is free fall? In the absence of air, all objects will fall at the same rate. Whether an elephant is jumping off from a hill or whether a small stone is dropped from a hill, both will be recording the same time period to reach the ground. In the same way, in the absence of acceleration due to gravity, in the same way, time period has no dependence on the value of mass of the object. Hence, we can say whether an elephant is swinging or ant is swinging, you can consider any object, whatever is swinging, doesn't matter, the time period of oscillation remains the same for the given length and at a given place. Then the second factor is that time period has no dependence with amplitude. In this expression, we are not getting any term related to amplitude of oscillation. So for smaller angle approximations, which means for smaller angles, the time period of oscillation is independent of amplitude. For larger angles, time period of oscillation has a dependence. So we are not going to speak about the larger angles here. For small angle approximations, the time period of oscillation is independent of the amplitude of oscillations. Here, time period has no dependence on mass. And second thing, time period is independent of amplitude for smaller angle approximations. So thus, we can conclude, when we speak about laws of simple pendulum, there are two factors to which the period of oscillation is dependent upon. One is law of length and another one is law of acceleration. So, law of length here states that, it gives out the explanation that the value of acceleration due to gravity is fixed at any particular place, then the time period of oscillation of the simple pendulum is directly proportional to the length of the pendulum. And second one is law of acceleration, where if the length of the simple pendulum is fixed, then the time period of oscillation of the simple pendulum is inversely proportional to the square root of acceleration due to gravity. And then the factors to which the time period of oscillation is independent on is also mentioned. So time period has no dependence on the mass of the object, means it has no relation with the mass. And then for smaller angle approximations, for theta being small, we can say time period is independent of amplitude of oscillations. Thus, the oscillation of the simple pendulum is studied, and we obtained the expression for the equation for a simple harmonic motion, which is a linear differential equation, d square x divided by dt square is equal to minus of omega square x. We obtained an expression as d square theta by dt square is equal to minus of g by L into theta. Both the equations are same. Both are linear differential equations, and we made an approximation over there. When you obtain the result, d square theta by dt square is equal to minus of g by L into sin theta. With the help of restoring force condition, we have sin theta. Sin theta is existing in the equation, which will not give this expression as a linear one. So this equation is a non-linear differential equation, which is a homogeneous second order equation. If sin theta is approximated to be theta, then the expression goes as d square theta by dt square equals minus of g by L into theta. Thus, this A is proportional to theta. A is proportional to theta. There is a proportionality coming directly with the theta. So we can say this expression is linear. This equation is a linear simple harmonic motion. This equation corresponds to a linear simple harmonic motion. So this is a linear differential equation, and the same second order differential equation but linear form. How this came? Based on this approximation, sine of theta is approximated to theta for smaller angles. Means if you make the pendulum to oscillate, if you make the pendulum to oscillate, you have to displace it through smaller angles. You should not take it to an angle of 90 degree or 180 degree. That won't result in a simple harmonic motion. In order to obtain simple harmonic motion from a simple pendulum, the angular displacement made, or the theta to which the pendulum is displaced, must be very small. So for smaller angle displacements, sine of theta is approximated to theta, so the equation becomes linear. Thus, we conclude that the oscillation of a simple pendulum is exactly simple harmonic. So, the pendulum executes a simple harmonic motion.